Artificial photosynthesis sounds like science fiction. Sunlight in, liquid fuel out. This prototype gives that idea a more concrete shape. In Osaka, a solar panel helped fill a bottle with a pale formic acid solution made from carbon dioxide, water, and sunlight. The part worth watching is how the machine handled a moving sun. As the panel's power rose and fell, part of the reactor warmed and changed its own electrical behavior, helping the chemistry stay matched to the panel. It treats the reactor as an active part of the solar system, tuned by the same heat and light that power the chemistry. The useful core of artificial photosynthesis is simple. Plants catch sunlight and store some of that energy in molecules. This machine chases the same storage goal with hardware: a solar panel, electrodes, a separator, pumps, and liquid reservoirs. The bridge between the two is chemical energy. Sunlight arrives unevenly. Molecules can wait. If a machine can turn some of that changing sunlight into a stable liquid chemical, it starts to solve a different problem from ordinary solar electricity. That is the frame for the rest of the video. Panels, chemistry, and a reactor that changes its behavior as the day changes. A solar panel is constantly changing. A cloud passes, the panel cools or warms, and the best mix of voltage and current moves with it. Chemists have to connect that moving power source to a reactor that wants to run in a controlled way. If the reactor asks for current at the wrong voltage, sunlight is still hitting the panel, but less of that energy reaches the chemistry. Engineers describe the panel with a current voltage curve, and the best point on that curve keeps shifting. For solar fuels, that mismatch is a real problem. The chemistry can be promising and still lose ground because the power source and the reactor are out of step. Normal solar systems handle the moving target with electronics. The panel has a sweet spot where voltage times current gives the most usable power. The name for following that point is maximum power point tracking, or MPPT. A converter sits between the panel and the load, constantly nudging the system toward that sweet spot. Batteries can also smooth the ride. That approach is mature and practical, but it adds parts. For a standalone chemical reactor, every converter, battery, sensor, and control layer becomes another thing to power, protect, and maintain. The question in this paper is sharper. Can some of that matching behavior come from the reactor materials themselves? The clever part sits inside the electrolyzer. The device uses a solid-state electrolyte, a separator that lets ions move while keeping the reaction zones organized. Its ionic conductance changes with temperature. When sunlight gets stronger, more current flows and the electrolyzer warms. As the separator warms, ions move more easily. That changes the reactor's impedance, which shifts the electrical load closer to what the solar panel can deliver efficiently. In everyday terms, stronger sun changes the reactor, and the changed reactor pulls power in a better way. Some of the tracking behavior moves out of a control box and into the material itself. Inside the reactor, each region has a job. On the cathode side, carbon dioxide is pushed toward formic acid chemistry. On the anode side, water oxidation balances the reaction. Between them sits the solid-state electrolyte, letting ions pass while keeping the two liquid streams organized. The separator is doing two kinds of work at once. Chemically, it helps control which products form. Electrically, its temperature-sensitive ion flow helps shape how the reactor draws power from the panel. The wiring still counts, but the material in the middle is doing more of the work than a simple divider would. The liquid in the bottle is formic acid solution. The solar panel supplies electricity, and the reactor uses that electricity to drive a chemical reaction with supplied CO2 and water. Formic acid is a real industrial chemical, and it stores energy in chemical bonds. The core reaction is CO2 reduction at the cathode, balanced by water oxidation at the anode. The result is a route from changing sunlight to a storable liquid molecule. The bottle is small, but the route is the point. If the reactor can make that route simpler, more stable, and easier to run outdoors, it becomes a useful piece of solar fuel engineering. The authors then took the system outside in Osaka. They used commercial monocrystalline silicon solar panels and 4 electrolyzers connected in series. Across one daylight period, the rig produced about 3.3 kilograms of roughly 3% formic acid solution, which corresponds to about 0.1 kilograms of formic acid. That is a small amount, but it came from a complete outdoor setup under changing daylight. The sun rose, clouds moved, power shifted, and the reactor kept making a measured product. The paper gives us outdoor behavior, real output, and a messier test than a clean lab curve. The two headline numbers measure different things. The reported PV energy utilization factor was about 85%, meaning the system kept much of the panel output engaged instead of leaving available power unused. The external solar to formic acid efficiency was about 2%. That number tracks the full path from incoming sunlight to chemical energy stored in formic acid, so it is much harder to move. Read together, the result is clear. The load matching idea looked promising, while the complete solar to fuel chain remains inefficient. One number tells us the panel and reactor were working together better. The other tells us how far the whole process still has to go. Now the limits. Battery-free refers to the main electrolyzer avoiding a conventional battery-based MPPT layer. The rig still used pumps, controls, a valve, a microprocessor, and peripheral power conversion. The carbon dioxide came from a supplied gas stream. The product was a dilute formic acid solution. Long-term durability still needs proof. Those details size the result. This is an outdoor prototype showing a smarter way to connect a solar panel and a chemical reactor. Commercial solar fuel would need higher efficiency, cleaner integration, stronger durability, and a sensible CO2 source. Solar fuels matter because molecules are convenient in ways electrons are not. Batteries are excellent when you want electricity back soon. Liquid chemicals can sit in tanks, travel through supply chains, and feed industrial processes. That can matter for shipping, seasonal storage, and chemical manufacturing. The technical goal is solar to chemical conversion. Take intermittent sunlight and store some of it in chemical bonds. This prototype is far from an industrial fuel plant, but it points at one of the hard control problems inside that vision. If the reactor can follow sunlight with fewer external layers, future solar chemistry systems could become less awkward to run. For this to matter beyond a prototype, several hard things have to improve. The electrolyzer has to last months or years. The carbon dioxide source has to be cheap and clean enough. Side reactions such as hydrogen and carbon monoxide waste current that could have made formic acid, that is the Faradaic efficiency problem. Product concentration, separation cost, and reactor materials also matter. Scaling an elegant lab system is where simple stories get expensive. The next important result may sound less dramatic than the first outdoor demo. Longer runtime, cleaner product, cheaper materials, and a reactor that keeps its performance after real wear. The takeaway is small, but it is specific. The paper shows a solar-powered reactor that made real formic acid outdoors while the sunlight changed, and the reactor materials helped with the load-matching problem. The efficiency was modest. The output was dilute. The scale questions are still serious, but the core idea is memorable. Instead of treating the reactor as a passive box attached to a panel, design the reactor so it participates in following the sun. The next tests are practical ones: longer operation, higher product concentration, lower cost, and proof that the material behavior survives outside the demo.